Hello team, in this video we're going to talk about building virtual networks. So virtual LANs are one of the simplest ways in which we can build virtual networks. So a VLAN is a tagging mechanism that is available on Ethernet switches. So a switch port can be part of one or more virtual LANs, and the switches only allow packets tagged with the correct VLANs to transit on those ports. And because the operator, like the cloud provider, is in charge of configuring the switch, then it can configure which tags go on which ports, and then we can control where traffic flows, and this is the mechanism that we will use to build virtual networks. So packets need to carry the correct VLAN tags to be sent on switch ports, and servers need to add these VLAN tags so that their packets go through. And the VLANs, because of this configuration and checking of the tags on each port, can provide isolation across ports, and this is again what we use to build virtual networks. So let's go over an example. So here we have a switch, and we have 5 servers connected to this switch. And these 5 servers are on 2 VLANs. So we have the blue VLAN, which is VLAN 1, and we have the red VLAN, which is VLAN 2. And here we see that the servers can have the same IP address on the different VLANs. So the blue VLAN has a server with IP address 1, and the second VLAN also has a server with IP address 1. So it's S1 on the blue VLAN and S1 on the red VLAN. And similarly, we have S2 on the blue VLAN and S2 on the red VLAN. So we can use the same IP address on both VLANs because the VLANs are completely isolated. So the IP addresses, they don't get confused. So let's consider that both servers S1 need to talk with both servers S2. So we're going to have 2 packets. So server S1 is going to send a packet, so the source is S1 and the destination is S2. And this packet is tagged with VLAN 1, right? Because this port is on VLAN 1, so only packets with this tag will transit through this port. So the server adds the VLAN and then sends the packet. And server S1 on the red VLAN will do the same. So it will send a packet from source S1 to destination S2, but now it will tag the packet with VLAN number 2, the red VLAN, and then it will go through this port. So if we look at these packets, they're very similar. They're exactly the same except for the VLAN tag. So these packets, they will arrive at the switch ports, and then the switch will see that the VLAN tags match the VLANs on the ports, and then the switch will forward the packets to their destinations. So the destination S2 on VLAN 1 is on this port, so this server will receive the packet, and destination S2 on the red VLAN is on this port, so S2 will also receive this packet. So there's no confusion on which server will receive which packet. Okay, but what happens if a malicious program tries to send a packet and spoof, falsify the VLAN tag? Say, for example, an application on server S1 tries to send a packet from server S1 to destination S2 on the blue VLAN. So it wants to send a packet to this server over here. So it shouldn't be allowed to do this because this server is on the red VLAN and this server is on the blue VLAN, so they should be completely isolated. But if the application on server S1 tries to send this packet, what will happen is the packet will go through the wire, and when the switch receives this packet, it will see that the VLAN tag is incorrect because this port is on VLAN number 2, the red VLAN, but the packet that it just received is tagged with VLAN 1 on the blue VLAN, but this port is not on the blue VLAN, so the switch will drop this packet and the packet will get discarded. So this malicious application didn't actually succeed in sending a packet to server S2 on the blue VLAN because the switch is in the middle and the switch dropped the packet. So again, this is an example of isolation between the 2 virtual networks. So in this example, we're talking about servers sending packets with VLAN tags. But we know that in cloud deployments, we don't have servers sending packets, we have virtual machines inside servers, and then each virtual machine can run multiple applications, and then these applications will send packets. So the picture is a little bit more complicated. So I have a switch, the server is connected to the switch. We don't have a single virtual machine on each server. We have multiple virtual machines. And now we need to isolate communication between these virtual machines as well. And in particular, when this blue virtual machine talks with this other blue virtual machine running on the same server, so these are virtual machines that belong to the same tenant, then we want to allow this communication to succeed. So this is okay. But when a green virtual machine wants to talk with a yellow virtual machine, so these virtual machines are on different VLANs, then we need to block this communication. So we also need to enforce isolation within each server. So how do we do this? So the main idea here is to also run a virtual switch inside each server. So this virtual switch that we have on each server is like a software switch, it's a piece of software, and it controls communication between the different virtual machines within the server and with the virtual machines within the server with the rest of the data center and the rest of the internet. So this is some piece of software that we control, and this virtual switch does the same checking that the hardware switch was doing. So it checks the VLAN tags or the VLAN identifier and then discards the packet if the tag doesn't match what's expected. So this virtual switch just does the same job as the hardware switch, but now also between the virtual machines within a server. And again, this virtual switch is managed by the operating system, which is managed by the cloud provider. So the cloud tenants have no control of what's going on in this virtual switch, just like with the hardware switch. So again, the cloud provider has control of where packets are going and can enforce isolation. So there are many network virtualization technologies. So we can use packet tagging, for example, the VLANs that I was just showing you. We can put tags inside MAC addresses. We can encapsulate packets, like we can create GRE tunnels, we can have MPLS tunnels. We're going to talk about VXLAN next. So there are many virtualization technologies for networks. We're not going to cover all of them, but what's important to understand is that all of these technologies, they operate on the same basic principles. First, packets need to carry something to identify which virtual network they belong to. So we need this information in the packet. And then the routing and forwarding of the packet is controlled by the network in a way that enforces isolation. So the network devices, the switches and the routers, they will look at this information in the packet that identifies the virtual network and then route the packet accordingly.